Have you ever wondered why the water molecule is bent, but carbon dioxide's is linear? Or why methane has a pyramid shape? The shape of the molecule determines everything about it, from how it reacts to whether or not it's poisonous. By the end of this video, you won't just memorize shapes, you'll be able to predict the 3D structure of any simple molecule just by looking at its chemical formula. This is the VSEPR theory, also known as the valence shell electron pair repulsion theory. It's one of the most powerful tools in chemistry. We're going to break this down into 3 easy steps. We'll quickly draw the basic Lewis dot structure. We'll count all the electron domains, and we'll use those domains to nail down the molecular geometry and bond angles. We're focusing on the core concepts today, but a quick heads up, to find the absolute most stable shape for complex molecules, you'll sometimes need an extra step called formal charges. We'll master that in a later video, but for now, let's unlock the world of molecular geometry. Let's go over the technique of drawing Lewis structures. First thing you need to do is decide which atoms are being bonded. Let's take an example of a compound such as CO3 2 negative. We need to count up all of its valence electrons. Remember that the valence electrons are the electrons in the outermost shell, consisting primarily of S and P electrons. Carbon is in group 14, so it's going to have 4 electrons. I have 3 oxygens. Each oxygen will have 6 valence electrons. I add those together. So 18 plus 4, that's 22 electrons. Now let's look at the charge here. That's a 2 negative, so I'm going to add 2 more electrons to that, so I have a total of 24 electrons. I decide which atoms are bonded together, so we've done that. We count up all the valence electrons. Now how do I know which one is the central atom? The one which is the lowest electronegative is generally the central atom. So we'll say that carbon is my central atom. We're just drawing a structural formula. Complete the octets for the atoms attached to the central atom. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. We're representing 18 electrons here. Remember that each bond is equal to 2 electrons. So I have 2 there, 2 here, so on and so forth. Okay, so therefore, we would have 18 plus 2, 4, 6. That gives us a total of 24 electrons here. Okay, so the central atom does not have a full octet. A few atoms do not have a full octet. Beryllium can only have 4 electrons. Boron and aluminum generally have 6 electrons. But all of the atoms in the second period otherwise must have 8 electrons. If you're in the third period or below, you can have more than 8. So carbon's in the second period, it must have 8. This rule says use double or triple bonds when there's not enough electrons. So I'm going to make a double bond here and take away these 2 electrons. Now the carbon has 2 here, 2 here, 2 here, and 2 here. It now has 8 electrons. If it's an ion, place square brackets around it and put our charge on the outside. Okay, there are some instances where I have too many electrons and I have nowhere to put them. So we'll use this rule when that occurs. Any remaining electrons, we'll place them around the central atom in pairs. We want to put these in such a way as they are as far away from everything else as possible because these electron pairs are very repulsive. We're now ready to start talking about valence shell electron pair repulsion theory. I prefer using the AXE notation, where A just signifies the central atom, X is the number of bonds, and E denotes the lone pair electrons. Okay, we will call these domains. Our simplest one here is domain 2. So a domain 2 would be AX2, which means I have a central atom and then 2 bonds. This will give us a 180 degrees or a linear molecule whenever this occurs. Some examples of compounds like this will be such as VeCl2, carbon dioxide, etc. Okay. Okay, on domain 3, I have an AX3 and I have an AX2E1. Okay, this is a planar molecule, and all the bond angles here are 120 degrees. And some examples here would be things like BCl3, AlCl3, SO3, CO3, 2 negative, nitrate. Those are some examples of AX3. It's a domain 3 because I have 3 bonds. Okay, on the right side here, I have an AX2E1. So this is my lone pair of electrons. Okay, this lone pair of electrons, they are very repulsive. So they're going to push everything further around, which means they're going to push this further around. So this bond angle here is going to be less than 120 degrees. Some examples of AX3E1 be like sulfur dioxide, ozone, TN2 chloride, etc. Okay, domain 4 would be AX4, AX3, E1, AX2, E2. So we have a tetrahedral structure, trigonal pyramidal, and angular bent. The bond angles will be 109.5 degrees for all of these, 109.5 degrees all the way around. Some examples be like methane, carbon tetrachloride, AX3E1 is called a trigonal pyramid. This is going to be pushing everything a little bit closer together. So these bond angles will be less than 109.5 for all those. These angles here will be little bit greater than 109.5. So examples will be compounds such as ammonia, PCl3, hydronium. Those are a few examples. And our last example here will be angular bent. We have two lone pairs now. Okay, so with two lone pairs, that means we're pushing everything even tighter together. And the bond angles are quite a bit less than 109 now. They're getting in the neighborhood of like 104, 105-ish. Okay, I'm going to put 105 degrees approximately. And some examples here will be things like water, okay. For domain 5, you have AX5, E0, AX4, E1, AX3, E2, AX2, E3. These three are all in a plane with the central atom. So everything within this triangle here will be 120 degrees. These will be 90 degrees. So I have a combination of 120s along the central plane, and then the one above the plane and below the plane will be 90 degrees. So some examples will be like PCl5, ASL5, and maybe SBL5. The next one, the AX4E1, we have a lone pair again. So this lone pair again is going to be pushing everything further around. So if you turn this thing sideways, it kind of looks like a seesaw. So that's why they call it a seesaw. It can also be called an irregular tetrahedron, a dysphoidal tetrahedron, and there are some other names like teeter-totter, so on and so forth. So some examples will be like SL4, TeCl4, IL4 positive. The next shape here is said to be T-shaped. Notice that we're losing our bonds or putting lone pairs along this central plane. I have two which are perpendicular now to the central atom. This one's perpendicular. This one's perpendicular. So those are 90s. We call this T-shaped. And of course, this will be perpendicular here. Examples will be ClF3, BrF3 be examples. The next case, I have replaced all of the atoms on the central plane with lone pairs. So again, I have a linear compound. So my bond angle is 180 degrees. So some examples will be like these compounds. The last domain that we'll be discussing will be domain 6. So it would be AX6, AX5, E1, AX4, E2, AX3, E3, and AX2, E4. Okay, so the AX6 is an octahedron, and all of the angles are 90 degrees on all the different planes. These four are in a plane around the central atom. Then I have a bond perpendicular up and one perpendicular going downward. So examples here could be like SF6, or maybe TeF6. In this domain, we'll lose our ones perpendicular to the plane first and replace them with electron pairs. So if I were to place an electron pair either on the top or the bottom, it would give me a square pyramid. So I have a square base here. If I would rotate this over, I would have one going up, which is a square pyramid. Examples will be BrF5, IF5. The next one is square planar. Again, we have a planar molecule, and there's four sides to it, so it's a square planar. So examples would be like the following molecules. The next one, AX3E3. There are no known stable compounds. However, there are some ligands that may exist that has this structure. All right, the last one is linear again, 180 degrees. And an example would be XeF2, for example. Let's try some examples. Okay, let's start with CO3 2 negative. Okay, we've already done it, but let's just go through it again. So counting my valence electrons, I can have 4 plus 3 times 6 plus 2. So it gives me a total of 24 electrons. So let's draw a skeleton. All right, let's place our dots. Okay, so counting the electrons, there are 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. But we said earlier that we need to take these two electrons and let's move them down here. So we're going to remove those two electrons. Okay. So I have 1, 2, 3 bonding sites. So it's AX3, E0. So for AX3, E0, I would have a trigonal planar. Okay, let's try H2O. I have 2 hydrogens. Each hydrogen has 1 electron, plus oxygen, which has 6 valence electrons, which gives me a total of 8 electrons. Hydrogen can never be the central atom, so the central atom will have to be oxygen. So I have a hydrogen on each side. This is not exactly drawn correct, but we'll fix it in a minute. Okay, so it's going to be an AX2 E2. So AX2E2 should be a bent or angular. To draw it more correctly, you want to place those electron pairs as far away as they can go and still remain symmetrical in the molecule. The next one, let's do ammonia. Nitrogen has 5 valence electrons, and hydrogens have 1. So that gives me 8 electrons. Nitrogen will be the central atom. So I have 2, 4, 6, 7, 8. So I have an AX3, E1. What that means is a trigonal pyramid. Okay, so let's try TeF4. Beryllium is in group 16, so therefore it's going to have 6 valence electrons. Fluorine is in group 17, so therefore it's going to have 7. I should get 34 valence electrons. The central atom is going to be beryllium. Let's put our electrons. That gives me 28 electrons that are being represented here. No, 32 electrons. I'm sorry, I can't add. So I need another pair, so I'm going to put them here or anywhere between any of these. So that's going to give me AX4 E1. So that's going to be an irregular tetrahedron, okay, or a seesaw. Okay, I3 negative. Okay, iodine will have 7 electrons in the outer shell, so it'll be 3 times 7. It has a charge of -1, so I'm going to add 1 electrons. That would give me 22 electrons. We'll come back to those later. Okay, so I have 8 plus 8 is 16. 17, 18, 19, 20, 21, 22. So it's an AX2 E3. All right, so an AX2 E3 is a linear compound. Okay, so xenon will have 8 electrons in the valence electrons, and fluorines are 7. So that should give me 36 electrons. So go ahead and populate my fluorines. That's 4 times 8, that's 32 electrons. So I have too many electrons. I'm going to put 2 here and 2 as far away as possible. So now I have 36 electrons represented. So this is going to be AX4 E2. So that is a square planar. I have 2 hydrogens. They're 1 each. Carbon has 4 valence electrons. Oxygen has 6 valence electrons. That should give us a total of 12 electrons. Carbon is going to be my central atom. That gives me 2, 4, 6, 8, 10, 12. The carbon here doesn't have its full complement, so I don't have enough electrons. So I'm going to take 2 electrons away and make a double bond here. All right, so I have an AX3E0, which means this is trigonal planar. Okay, iodine has 7, and chlorine has 7. So 4 times 7 is 28 electrons. Let's start populating electrons. That's 24 electrons. 25, 26, 27, and 28. So this is going to be an AX3E2, which will be T-shaped. Okay, SeO2. Okay, Se is in group 16, so it has 6 electrons. Oxygens also have 6. So 12 plus 6 is 18 electrons. So populating our electrons. All right, so 2 to 8 is 16 electrons. 17, 18. I don't have enough electrons to run a selenium. So one of these oxygens is going to have a double bond. So it doesn't matter which one you choose. I'm going to choose this one and place a double bond here. So I have an AX2E1. So AX2E1 means it's going to be a bent molecule or angular. ASF5. Arsenic is It's in group 15, so it'll have 5 electrons. Fluorine will have 7. That should give me a total of 40 electrons. I got 5 times 8 is 40. So I have an AX5E0. This will give us a trigonal bipyramid. That's how we use Lewis structures and valence shell electron pair repulsion theory to predict the shapes of simple molecules. Once you can draw the Lewis structure and count the bonding in lone pairs, the molecular shape almost reveals itself. If this video helped you understand molecular shapes, give it a like, subscribe for more chemistry tutorials, and let me know in the comments. Thank you for watching. Goodbye.